This is section 1-2, part B, analyzing graphs of functions and relations. Your I can statement for part B is going to be I can explore symmetries of graphs and identify even and odd functions. So graphs have symmetry. There are different types of symmetry they can have. The first type is line symmetry. A graph that can be folded along a line and the two halves match exactly is a graph that has line symmetry. If a graph can be rotated 180 degrees with respect to a point and it still remains unchanged, then that graph has point symmetry. We have some specific types we're going to look at. The first type is a symmetric with respect to the x-axis. We know our graph is going to be symmetric about the x-axis if you can fold it over the x-axis and it matches up. We also can look at this from points if you don't have the graph. And if we have a value of x and positive y, and we also have a value of x and negative y, then it would be symmetric about the x-axis. Now, an example of this would be on this, if we said this was a value of 2, positive 2 up here, this point down here is 2 and negative 2. The x values are exactly the same. The y values have the same number but different signs. So this would indicate that it's symmetric about the x-axis. We know a graph is symmetric about the y-axis if we can fold it across the y and the two sides would meet. Also, if we look at our graph, if we have the value of xy, we also have the value of negative x, positive y. So if we have the value of 1, positive 2, we would also have the value of negative 1, positive 2. The y values are exactly the same, but their x values, one is positive, one is negative, but they have the same value. That would indicate that we are symmetric about the y-axis. If we're symmetric about a point, the first one we usually discuss is symmetric about the origin. That means we can pick up the graph, rotate it around the origin 180 degrees counterclockwise. When we set it back down, it's still going to look exactly the same. We're going to know it's symmetric about the origin if we have the point xy, and we also have the point negative x, negative y. So up here, if this point is positive 2, and the point down here is negative 2, negative 2, we have the same number but different signs in both locations, so that would be symmetric about the origin. Now if we take a look at this graph, you first can indicate what type of symmetry we have, but then we're actually going to have to show that numerically. So if we take a look at the graph, we can fold it across this x-axis and the two halves would match up. So this should be symmetric about the x-axis. Now to show this, we're going to plug in some numbers. You want to find values that are actually on the graph so that we know that they work. So you're going to pick x values that are on the graph and solve for the y. So let's let x equal 2. If x is 2, we're going to substitute it into our equation and we're going to solve for y. So the first thing we're going to do is we're going to subtract 2 from both sides. We're going to divide both sides by negative 1. Now we have y squared is equal to 1. To get the y by itself, we're going to take the square root of both sides. But remember, when you take the square root, there is a positive and a negative answer. So y is equal to positive or negative 1. So on the graph, we have the coordinates of 2, positive 1, and we have the coordinates of 2, negative 1. With these numbers, we are indicating that this is symmetric about the x-axis because the x numbers are the same, but we have y values that are the same number but different signs. So this is symmetric about the x-axis. So when we look at graphs of functions, we can have graphs that are symmetric about the x-axis or the origin. Then these types are also can have different special symmetries. They can be even functions or they can be odd functions. Even functions that are functions that are symmetric with respect to the y-axis, and we know that f of negative x is equal to f of x. So that means if I replace each of my x values with a negative x and I simplify my equation, it'll still look exactly like it did before I started. We know that a function is odd if it is symmetric about the origin. And if we plug in a value of negative x, when we're done, the new function will just be a negative version of the original function, which means all the signs will change. So if we graph this function, the graph should look roughly like this. And if we notice, we could pick up this graph, I could turn it 180 degrees, sit it back down, and it should still look exactly the same. So this should have symmetry about the origin. But we're going to show this with our math. So we're going to plug in a value of negative x. So wherever you have an x value, you're going to replace those values with a negative x. And now we're going to simplify and see what happens to the graph. Negative x to the third power. Negative 1 to the third power is still negative 1, so this is still going to give me negative x cubed. Negative 2 times negative x is going to give me a positive 2x. Now if we look at our new equation, when we look at our original equation, you notice that each of the signs changed. We went from a positive x cubed to a negative x cubed. We went from a negative 2x to a positive 2x. Since both signs changed, that means this is an odd function. Which is also what our graph showed. Because the graph is symmetric about the origin, it should be an odd function. If we would have plugged in a negative x, and it would have looked exactly the same when we were done, so if it would have still looked like x cubed minus 2x after we simplified, that would have been an even function, which indicates that it's symmetric about the y-axis.